Blackbody radiation. Very hot objects appear to glow. This phenomenon is observed throughout our daily lives. When we switch on the stove, it glows red. Even the sun, which is always at a very high temperature, emits the light that reaches us on Earth. In fact, Kirchhoff's radiation law states that all objects at every instant are absorbing radiation falling on them and re-emitting electromagnetic radiation. But why is this the case? No object is at absolute zero. Resultingly, the constituent atoms and molecules are always vibrating from thermal energy. From this vibration, electrons are moved from their lowest energy, or ground states, to higher energy, excited states. Afterwards, they return to their ground states and release the additional energy as electromagnetic radiation. That is to say, the vibration of charged particles, which matter is comprised of, causes thermal radiation. Objects at higher temperatures have more thermal energy, and thus they emit higher energy, high-frequency radiation. Unlike other forms of electromagnetic radiation, however, thermal radiation is not of a single frequency, but over a spectrum of different frequencies, with most of the radiation coming at a peak. Since it is a form of thermal radiation, this peak frequency is dependent on the temperature. A black body is a theoretical object which does not discern frequencies of light to absorb through reflection or transmission, absorbing all incident radiation. Due to Kirchhoff's radiation law, this is fully converted into heat, which is then translated back into electromagnetic radiation. That is, a perfect absorber of light is also a perfect emitter of light. Before progressing, it must be understood that a black body is not necessarily black in color. It can be of any color. Remember, the black body is always emitting radiation. It may, however, be outside of the visible spectrum, appearing black, hence the name. During the late 19th century, physicists were challenged with figuring out how much of each frequency band of radiation was being emitted by a black body. They strived to describe the mathematical relationship for the energy of this thermal radiation per unit volume, which is called spectral radiance at a given temperature. This can be called the blackbody distribution law. In the year 1878, American scientist S. Langley invented the bolometer, a radiation measuring tool. From this, he was able to provide empirical results to the relationship between radiance, temperature, and frequency of the electromagnetic radiation emitted by a black body. The distribution curve of a black body is as follows. The intensity of different wavelengths of radiation at multiple temperatures are shown. Notice that as the temperature increases, not only does the intensity of the light increase, but the peak wavelength, signified by the blue dot, shifts towards the left. From this, as well as building upon thermodynamics reasoning from Boltzmann, in 1893, German physicist Wilhelm Wien discovered Wien's law, that is, the peak intensity wavelength is proportional to 1 upon T, where T is the temperature. Thus, lambda peak equals Wien's constant over T. As the temperature increases, the peak wavelength decreases, explaining the shift to the left on the curve. Stars can be approximated as black bodies. The spectral sequence supports Wien's law, as hotter stars have a lower wavelength, being blue, and cooler stars have a higher wavelength, being red. Notice again that the peak wavelength increases rapidly as the temperature increases. In 1879 to 1884, Austrian physicists Stefan and Boltzmann found this relationship to be modeled as luminosity, or radiance, equals Stefan-Boltzmann constant times T to the power 4. Using this, we were able to calculate the surface temperature of the Sun for the first time, approximating it to be a black body and measuring its luminosity. The first attempt to find the blackbody distribution law was done by Wien in 1896. Black bodies are theoretical, but he considered an enclosed oven painted with lamp-black paint a great absorber of light, with a small hole in the side. All radiation that enters through the hole will bounce around the oven, being absorbed on every reflection. Thus, almost all radiation of any frequency is absorbed, approximating a black body. From classical thermodynamics reasoning, Wien treated electromagnetic waves as ideal gases. His relationship is now known as Wien's approximation. He explained that spectral radiance was equal to A times the cube of frequency times e to the minus b nu upon t, where A and B are constants and nu is the frequency. Graphing the relationship is as follows. As seen, this is a good approximation for high frequencies, but there was a fundamental problem. It did not support the experimental results at low frequencies. This discrepancy could be mathematically explained after the correct radiation law was found, and will be explained shortly. The next attempt was by Englishmen Rayleigh-Jeans in the years 1900 to 1909. They considered blackbody radiation to consist of standing waves, which are produced by molecules vibrating at a set frequency. That is, the molecules in the walls of the black body were acting as harmonic oscillators and creating standing waves of specific frequencies. The transverse standing waves had nodes at either end of the box, where the harmonic oscillators were producing the wave. The amplitude of the standing wave is completely diminished at either end. From this, there must be an integer number of half wavelengths, namely, length over half of wavelengths equals n, where n is an integer. For example, standing waves with n equals 1, 2, and 3 are shown. Rayleigh-Jeans found the amount of standing waves in a small frequency band, nu to nu plus d nu, to be 8 pi nu squared upon c cubed, by considering the standing waves of integer wavelengths in a cubical cavity. However, there can be more than 10 to the 4d standing waves of different energies, so it is not viable to sum their individual energies. From classical thermodynamics, the theorem of equipartition says that the energy of motion is equal for each degree of freedom, where each is given the energy E equals half kT, where K is Boltzmann constant. A degree of freedom is simply a way in which a molecule can move, rotationally, linearly, and so on. In the black body, the transverse standing waves have 2 degrees of freedom surrounding each of their nodes. Equipartition allows us to give each of them an average energy of 2 degrees of freedom times half kT equals to kT. Thus, Rayleigh-Jeans black body law is spectral radiance equals 8 pi nu squared upon c cubed times kT, the number of standing waves times their average energy. This relationship is known as the Rayleigh-Jeans black body radiation law, and supports the experimental results for low frequencies, where WIEN'S law failed. However, Rayleigh-Jeans law said that at a given temperature, the radiance is proportional to the square of the frequency. As we increase our frequency, radiation keeps growing and goes to infinity. This theoretically means that the energy of a black body is infinite, and all bodies are always radiating infinite amounts of high-frequency ultraviolet radiation. From this, if you were to put some bread in your toaster, it would be burned to a crisp by intense ultraviolet radiation. This fatal flaw was dubbed the ultraviolet catastrophe. Einstein argued that Rayleigh-Jeans law was outrageous in 1905. At this point, there were 2 theories as to the blackbody radiation law: WIEN'S approximation, which failed at low frequencies, and the Rayleigh-Jeans law, which failed at high frequencies. In the year 1900, German physicist Max Planck attempted and succeeded in finding the blackbody distribution law. Rayleigh and Jeans were correct in their number of standing waves, but were incorrect in their use of classical mechanics to say that the average amount of energy per wave, E, equals to kT. This is what caused the ultraviolet catastrophe. Rayleigh and Jeans had assumed that harmonic oscillators in the blackbody could produce waves with any energy along a continuum. Planck postulated that this energy could only take upon discrete values. Standing waves with integer half wavelengths could only have discrete frequencies and energies. Namely, total energy equals nh nu, where h is Planck's constant and n is an integral amount of waves. This led to the idea of a photon, or a packet of light. Originally, quantization was done heuristically, to make Planck's maths work. Later, the idea of a quantum harmonic oscillator justified this. There are different thresholds of activation at a discrete number of frequencies. These levels are further apart for high-frequency radiation. Thus, they are harder to activate and do not get activated as frequently. This resolved the ultraviolet catastrophe. To find the average energy per wave, Planck then used the Bose-Einstein distribution, which gives the probability that any wave in the distribution is of the given frequency, as well as its energy of a single standing wave equation from earlier, E equals to h nu. This is substituted into the Bose-Einstein statistics as seen. Combining these, Planck's law then becomes spectral radiance equals 8 pi nu squared upon c cubed times h nu upon e to the h nu on kt minus 1, giving the correct blackbody distribution law, matching the experimental results. Notice, this looks incredibly similar to WIEN'S approximation. WIEN'S approximation only worked when h nu was much greater than kt, as then 1 over e to the h nu upon kt minus 1 was approximately equal to e to the negative h nu upon kt, as in WIEN'S approximation. Not only was Planck's law successful in explaining the blackbody distribution curve, but was a breakthrough for physics as a whole. Considering energy to be exchanged in discrete amounts is known as the quantization of energy. This discovery has consequently led to the field of quantum mechanics and has many real-life applications. Using Planck's work on blackbody radiation, the mechanics of a light bulb is explained. Again, it is a hot object radiating light, albeit not to the same extent as a black body. The study of blackbody radiation led to the discovery of cosmic microwave background, which is blackbody radiation at a temperature of 2.725 Kelvin. The spectral emission of light at different temperatures explained by blackbody radiation allows us to use infrared thermal cameras. In the current pandemic, these are used at airports to check the temperatures of passengers efficiently. Explaining the blackbody radiation curve was the first step to the discovery of quantum mechanics, which is an upcoming field that revolutionizes physics as we know it today. Thank you, Jerry Mahajan.